So, hello students, welcome to QUARRIES classes. So, in this video, we are going to discuss about Riemann integration. Riemann integration is one of the most easiest topic in mathematics. Integration means area, and Riemann integration means we are going to find area of a curve, area under a curve. Okay, there will be a bounded curve, so which will looks like something like this. Let this be an there will be a curve something like this, and we are going to find the area of this portion. Okay, this is our target. Okay, so this area actually known as Riemann integration of this function. Okay, of this function. Okay, so for this, now we are going to before starting this chapter, we need some definition. The first definition is partition. Okay, let AB closed interval AB be a closed and bounded interval. Okay, this is a closed and bounded interval. Okay, so let this be our number line, and this is our A and this is our B. Okay, a partition on closed interval AB is nothing but a set of finite number of points which have an ordering. Ordering means which if we are going to find a partition on this interval which will look like this, some finite number of points whose initial point starts with A and the terminal point is B. So if we choose a partition which initial point is x0, then x0 is A, this is our x1, this is our x2, this is our x3, this is our x4, this is our x5, and the terminal point x is the end point of this interval. So a partition on AB is a finite order set. It is denoted by x0 less x1 less x2 dot dot less xn, where x0 is equal to A and xn is equal to B. Okay. Now let's talk about Riemann integrability and where we need this partition. Okay, suppose this be a function. This be our closed and bounded interval AB, and this be our function f. Okay, now we can see that we have chosen a bounded function and it is also continuous function. Okay, now so if we choose capital M is equal to supremum of fx, x belongs to closed interval AB, so we are considering capital M as the maximum value of fx. So according to our picture, this is something our capital M, right? This height is our capital M. Now if we are multiplying this capital M with B minus A, that is the length of this interval, then we are finding we got the area of this rectangle, right, which has this portion. So this is not the area of this rectangle is not the area of under this curve, right? So for this, what I am going to do, I am going to taking the minimum value of f also. That small m is equal to infimum of fx, x belongs to closed interval AB. Okay, so according to our picture, this is our small m. Now if we multiply this small m with B minus A, we will get the area of this rectangle, right? This rectangle, right? Now again, this area is not equal to the area under this curve. So then what we are doing, we are taking the average of these two average of the areas of these two rectangles. Then we will get an area of rectangle which will looks like this. But again, this is not the perfect area under this curve. So for this, what I am going to do to get the perfect area, what I am going to do, I am going to take a partition on this interval. Okay, so now look at the picture. Let this be our A, this be our B, and this be our function f. Okay, this be our function f. Now we are considering a partition whose initial point x0 is equal to a. This is our x1, this is our x2, this is our x3, and this is our x4 is equal to b. So we are considering a partition p is equal to x0 less x1 less x2 less x3 less x4, where x0 is equal to a and x1 is equal to b. Now observe that in this interval from x0 to x1, this is the supremum, this height is the maximum height, and this height is the minimum height. So what I am going to do, I am going to take capital MR is equal to supremum of fx, x belongs to x r minus 1 xr, where r starts from 1 to up to 4. Okay, and small mr is equal to infimum of fx, x belongs to x r minus 1 xr. Okay, r is equal to 1 to up to 4. So now according to our picture, this is our capital M1. This is not completely visible. This is our capital M1 and this is our small m1, right students? And this is our capital M2. This is our small m2. Okay. Now if we multiply this capital M1 with the length of this x0 to x1, that is x1 minus x0 with capital M1, then we will get area of a rectangle, area of this rectangle, right? Now in the previous picture, when we are considering about this area, we will get we got some errors, right? This is the error. Now in this picture, when we are considering this smaller portion, we were getting some error like this. So the error of this picture is lesser than this one, right? Now again, when we are going to multiply this m2 with this interval, length of this interval, then we are considering about the area of this rectangle. Again we got this error, right, which is the more lesser, which is lesser than the previous one, right? So when we are considering a partition, or when we are cutting the interval, cutting closed interval AB in more smaller portion, then we are getting lesser error, right? So this is the idea behind Riemann integration. Okay, now let's consider some definitions. Okay, so okay, let fx be a bounded function. Fx be a bounded function. Okay, on closed interval AB. Okay, now and let a equal to x0 less x1 less x2 dot dot less xn is equal to b via it is equal to p via partition on closed interval AB. Okay, this is a partition on closed interval AB, and let capital MR is equal to supremum of fx, x belongs to x r minus 1 xr. Okay, r is equal to 1 to up to n, and small mr is equal to infimum of fx, x belongs to x r minus 1 xr. Now observe that this capital mr and small mr varies when we are changing the partition. Okay, now suppose we are going to multiply capital M1 with the length of this interval x1 x0, that is x1 minus x0, then M2 with x2 minus x1, in such a way with Mn with xn minus xn minus 1, right? This value is known as upper sum upper sum of f corresponding to the partition P. Okay, upper sum of f corresponding to the partition P. It is uh, denoted by UPF. Okay, and small m1 with x1 minus x0 plus small m2 with x2 minus x1 in such a way small mn with xn minus xn minus 1 is known as lower sum of f corresponding to the partition P. It is denoted by LPF. Okay. Now observe that for a fixed partition P, UPF is nothing but a real number, and for a fixed partition P, LPF is nothing but a real number. Now we are considering two notations. Integration lower bar integration a to b lower bar fx dx is equal to supremum of LPF such that P belongs to script P AB. Script P AB means set of all partition on closed interval AB. Okay, and upper integral a to b fx dx is equal to infimum of UPF such that P belongs to script P AB. Okay, now this is the definition of lower integral, which is equal to supremum of LPF. P belong to script P AB, and this is upper integral, which is equal to infimum of UPF such that P belongs to script P AB. Observe that when you are changing the partition, you are getting UPFs, okay, which are equal to a real number. For a fixed partition P, UPF a real number. Now this set is a set of real number, okay, which is bounded below, and for this set we are considering a infimum, okay, and this set is a set of real number which is again bounded above. We are considering the supremum of this set as lower integral fx dx, and this is as upper integral fx dx. Okay, now if there exists a partition P, now if the value of this upper integral a to b fx dx minus lower integral a to b fx dx is less than epsilon for any epsilon greater than 0, in other word the value of this upper integral a to b fx dx is equal to the value of this lower integral a to b fx dx, then we say that f is remain integrable. Okay, if the value of the upper integral is equal to the value of the lower integral, then we say that fx is remain integrable, and the value of this integration is equal to integration a to b fx dx, which is equal to the value of the upper integral as well as lower integral. Okay, so this is the formal definition of Riemann integration. Okay.